and starting to become familiar with the idea of the mole. The mole is the central unit of measurement to represent and compare quantities of substances in a reaction or in a system. So a mole can represent mass. 1 mole equals the GFM of a substance. 1 mole can also represent a count. So 1 mole represents a count that contains 6.02 times 10 to the 23 particles. So that's a pretty big number. And 1 mole can also represent the volume of a gas. So 1 mole of a gas will occupy 22.4 liters of any gas as long as it's being held at STP. So let's start with the gram formula mass. I referred to it as the GFM. The gram formula mass is also called the molar mass or formula mass. It is simply the sum of the masses of all the atoms present in the chemical formula. So we need to be consistent in how we calculate the gram formula mass. So what we use are the atomic masses listed on the periodic table, and we need to round those to the nearest tenths place. And simply, we multiply that atomic mass that's been rounded to the tenths place and the element's subscript. So the first thing I want to look at is the rounding. I want to make sure that we all have the same idea about rounding to the tenths place. So when you look at oxygen's mass as listed on the periodic table, it's 15.99994. So we're going to keep all the digits left to right down to the 9 or to the tenths place, which is this digit of 9. So we're going to put the bar above the digit in the tenths place because that's going to be our most right, quote unquote, sig fig. But what we have to do is we have to take a look at it, and the next digit, which is in the hundredths place, doesn't make the digit in the tenths round up. And in this case, because that digit is 5 or greater, it makes it round up. So we would record oxygen's mass 16.0 because it has to be recorded to the tenths place. Even if it's a digit of 0 in the tenths, it needs to be recorded. So looking at the next example, sulfur, atomic mass on the periodic table is 32.065. We need to keep the digits left to right down to the tenths place, so the 3, the 2, and the 0. So our most right sig fig is in the tenths, and we take a look at the digit that's in the hundredths. Does it make the digit in the tenths round up? Yes, it does, because 6 is greater than 5. So we would record and use sulfur's mass as 32.1. Our most right digit is in the tenths position. Okay, let's take a look at a couple of the you-dos. So we take a look at phosphorus's mass as shown on the periodic table, 30.97376. We keep the digits left to right all the way down to the tenths place, so that is a 9. We take a look at the digit in the hundredths. Doesn't make the 9 round up? Yes, it does, because it is greater than 5. So we would record phosphorus's mass as 31.0. Potassium, when we take a look at it on the periodic table, its mass is recorded as 39.0983. Once again, left to right, we keep all the digits down to the tenths position, and we have to look at the digit in the hundredths. Does that digit in the hundredths make the digit in the tenths round up? And in this case, it does also, because 9 is 5 or greater. So for potassium, we would record its mass as 39.1. You do A and B, and check your work with your instructor. Now, calculating the actual GFMs. You need to show this work. This is the correct numerical setup. Many times on exams, you will only be graded on your GFM work and not on a final calculated answer. So let's take a look. In order to come up with the gram formula mass, molar mass, or the formula mass, you have to have the correct mass or the correct chemical formula of the substance. So our substance is zinc. So zinc represents an individual element, and it is not one of the special 7, so it's monatomic. So the chemical formula, I understand, is simply Zn. So in this chemical formula, I have 1 zinc, which would be its subscript, and I multiply it by its mass rounded to the tenths. So when you look at the mass of zinc, it rounds to 65.4. And that's it. It's just that one atom that contributes mass. So the GFM for zinc is 65.4, that should be a 4, grams, and that is the mass of 1 mole of zinc. So 1 mole of zinc has a mass of 65.4. The next substance says a nitrogen molecule. Well, nitrogen is an individual element like zinc, but nitrogen is one of those special 7, so it's a diatomic. So its chemical formula is N2. So you got to have the correct formula. So in this chemical formula, there are 2 nitrogens. And when you look at nitrogen's mass on the periodic table, it would round to 14.0. So I have to have that digit in the tenths place. So there's only nitrogen in this formula, and there are 2 atoms of it. So my math is simply 2 times the 14.0. Pretty simple math here. So the GFM of nitrogen is that there are 28.0 grams of nitrogen in 1 mole of nitrogen. Move this up a little bit. Okay, next substance. When we take a look at it, it says magnesium oxide. So this is a compound. So I need to change this chemical name into a formula. So when I think about the process, my symbol for magnesium is Mg, and my symbol for oxygen is O. But magnesium uses a +2, oxygen uses a -2. So when I do my crisscross, I end up with a 2 to 2, which reduces to a 1 to 1. So my chemical formula for magnesium oxide is MgO, which means I have 1 magnesium and its atomic mass rounded to the tenths place is 24.3. So this belongs to magnesium. Now I need to add that to what the oxygens contribute. There's 1 oxygen, and it contributes a mass of 16.0. Got to have that digit in the tenths place. So the mass of the 1 magnesium added to the mass of the 1 oxygen leaves me with a GFM of 40.3 grams of the magnesium oxide, and that's the mass that would occupy 1 mole of magnesium oxide. Okay, taking a look at this next substance, calcium phosphate. So this is a compound, and I notice ATE, so that means I have a polyatomic ion. So I know I need to look at my table E, and when I look it up, I know that phosphate is PO4, And calcium, according to table S, uses a symbol of Ca. I look up the oxidations. Calcium uses a +2, phosphate a -3. So I crisscross those magnitude of those charges. So in calcium phosphate, for every 3 calciums, there are 2 phosphates. So I have my correct chemical formula. I have 3 different elements. So each one needs to be individually shown in the correct numerical setup for calculating the GFM of this compound. So in my chemical formula, there are 3 calciums, and each one contributes a mass of 40.1. Plus, now, inside the parentheses, I have 1 phosphorus, but there are 2 units of this. So if I was to draw this down here, it says I have a PO4 and another PO4. So each phosphorus unit, there's 2 of these phosphate units, each one contains a phosphorus. So 2, the subscript on the outside, times the subscript of 1 on the inside. I have a total of 2 phosphoruses in this compound, and each one contributes a mass of 31.0. Now my last and final element, oxygen. So inside the parentheses, there's a 4, but there's 2 of those units. So I have 4 in this phosphate and another 4 in this phosphate. So subscript inside the parentheses times the subscript outside the parentheses, it's a total of 8 oxygens, and each one contributes a mass of 16.0. So in my calculator, 3 times 40.1 plus 2 times 31.0 plus 8 times 16.0, hit your equal sign. So the GFM, compared to the other ones, it's pretty big. So it's 310.9 grams equals 1 mole. So I need to erase this down here at the bottom. I'm going to need a little bit of room. Okay, so the last example here is a hydrate. So I can tell that because I see the word hydrate here. So a hydrate is simply, we have a salt that is surrounded by a certain number of waters. It is the GFM of the salt plus N times the GFM of the water. This is not multiplication. It's the salt, big fat dot, which means it is surrounded by a certain number of water molecules. So I'm going to deal with the salt here. So in this case, barium chlorate, this is the salt. So that's what I'm going to do first. So barium sulfate compound. I have chlorate, which is a table E guy. So that would be ClO3. Barium is Ba. Barium uses a +2. The chlorate a -1. So when you crisscross, I need 1 barium for every 2 chlorates. So here we go, the GFM of the salt. So the GFM salt, I have 1 barium, and it contributes 137.2 grams. Plus, now inside I have 1 chlorine inside the parentheses, a 2 outside, so that means that there's a total of 2 chlorines, and each chlorine contributes a mass of 35.5. And now I move on to the last element in the salt, which is oxygen. There are 3 inside the parentheses, and there's a 2 outside, so 3 times 2 means there's a total of 6 oxygens, and each one a 16.0. Now we're going to keep adding here. Now we're going to add to the GFM of the salt, we're going to add the water. So the GFM of the NH2O. Now, I want you to memorize the GFM of water. So we're going to get this memorized. This is the only time we're going to write it out. The GFM of the water. 2 hydrogens each contribute a mass of 1.0 plus the only oxygen 16.0. So the GFM of water is 18.0 grams. N is the number of waters. So right here we have di, that is N, and as you know, di means 2. So I have the GFM part of the salt plus, for N, I'm going to substitute in 2 waters, and each water contributes 18.0 grams. So we have the salt's GFM plus the addition of the 2 waters. So when you put this into your calculator, the GFM of this hydrate is 340.3 grams of this hydrate in every mole of this hydrate.